Good morning. Good morning to everyone.
Oop.
Thank you for the invitation.
It's a bit slow, but it will pop up your presentation. Here it comes.
Okay. Working? Is visible?
Yes, yes.
Yeah. Thank you very much for the invitation to join in this interesting webinar. Today, we will want to talk you about the role of soil in a nature-based solution, and in particular in how we can bridge two very interesting key policy framework: soil monitoring law and nature restoration regulation. And the message that I want to leave is that the soil is not just a part of nature-based solution, but it determines if nature-based solution work or not. As you know, nature-based solutions are increasingly central for a lot of action to protect, restore, and manage ecosystems. So they assure the functioning of climates and all and are the instrument for biodiversity challenge, but they depends main on soil-mediated process. So we have a lot of on soil-mediated process like carbon storage, nutrient cycle, loss, maintenance on biodiversity, water regulation. And all of this leads to a key point. So soil health is the precondition for an NBS effectiveness. And however, as a soil scientist, I have to say that the soil is still really treated as a primary driver of nature-based solution performance. So give an overview that our understanding of soil has evolved significantly in the last century. We have moved to from a productivity-based view towards a system perspective. We have a shift toward function and resilience, and now soil in this moment is viewed as a living system that provides function that supporting resilience. And this concept aligns with the NBS framework that are function-based. So soil is not a passive substrate, is an active system, and we have to remember that it is a complex system, especially in the monitoring. In fact, the soil monitoring consistently with soil health evolution has not kept pace. In fact, now currently soil monitoring systems are universally fragmented, poorly harmonized, and for what concerns nature-based solutions are weakly connected. And this creates a problem because monitoring is the main bottleneck for NBS approach and effectiveness, because we can properly evaluate nature-based solution outcomes if we will not consider soil monitoring. When we look what happened in soil indicators evolution, we have seen an imbalance until more or less 20 years, because we have a loss of monitoring system based on chemical and physical indicators, while the biological properties are still underrepresented. Unless there is a recent increase in soil biological monitoring, especially in scientific literature in the last 5-6 years, because there are a lot of advance for biological techniques, molecular techniques, and AI-driven digital soil mapping. So this is critical because the biological process of soil now has been important in soil science, but not in all system monitoring. And if we consider what the NBS soil are linked, we have in this diagram are indicated of how NBS and soil are connected, because it is a bidirectional function. Because if NBS give system to provide the function of soil regulate the soil properties, but NBS are an approach to prevent soil degradation. And we need to monitor the different indicators to evaluate if NBS approach work or not. In fact, with no indicators, we cannot evaluate the function. And if we not evaluate the function of soil, we cannot have a policy impact. So soil indicator is not a technical tools, but is the bridge between science, NBS, and the policy. At the EU level, in the last years, we have seen a rapid convergence from Green Deal, since Green Deal in 2019, and we have from this part the two main policy framework, Natural Restoration Law and Soil Monitor Law, that has been started. So in this framework, we have recognized soil concept, all the ecosystem function, and the NBS approach for ecosystem restoring. But there is this moment a gap between policy ambition and scientific implication. This happens if we see how the EU soil strategy that has been started in 2021 has set a vision for 2050. And from this soil strategy, we have seen that soil is now proposed as a compartment with the similar to water and air, and has been encouraged a specific regulation. Soil has been recognized for the impacts to provide ecosystem service. And this strategy has been set the concrete action and is the pillar for the reference for natural restoration regulation and soil monitoring law. The vision was set was to have healthy soil by 2050 and set a lot of concrete action. The restoration law has been the first pillars that was implemented in 2024, and in this regulation, soil health and NBS approach are explicitly included. So we have this ambitious target also to restore at least the 20% of EU land and sea areas by 2030, and all ecosystem that need the restoration by 2025. This is very important because in all this objective, we have seen that this regulation has provided some specific targets for different ecosystems. So we have marine ecosystem, river ecosystem, like also agricultural ecosystem, forest, urban ecosystem. And for example, if we look to agricultural ecosystem, we can see that we have some specific indicators that give the idea to that are the threshold to restore the ecosystem. I don't know what happened. Sorry. And if we look to these indicators, we see that soil organic carbon is one of the main indicators that has been proposed and applied to recover soil health. And we can pass to the soil monitoring law that has been entered the force in the last month at the end of 2025, after a long discussion with the Parliament and Council. But now we have that this law give a mandatory monitoring for all member states. And this law has been set a common set of EU indicators for physical, chemical, and biological soil health. Also indicate management for contaminated sites. It is also provided that this law has been transposed by member states in the next years, and it is provided that by 2032 we have the first reporting of soil health status for all EU. For a USA, and it is provided a revision after this reporting. If we see what is, this is a table that describes what are the indicators that are divided in different level of application. We can see that we have some indicators that are set at EU level and are mainly chemical and physical. We have other indicators that are set at the level of member states. And we have another set of indicators that are based on voluntary indicators. And biodiversity and all biological property of soil are evaluated only at this level. So we can see that we have also a weak on biological evaluation of soil, and there is also a lack of functional integration in this framework. In fact, we have, from this point of view, an underrepresentation of soil biological indicators. And there is also some problems about methodological methods that have been applied to compare soil health evaluation in all regions. So we need a minimum set indicators that was provided in we have a first starting point in this monitoring system, but we need also to harmonize because we have soil biology and biodiversity, and especially all ecological functional are provided, but we have to understand how it can be implemented in the next years. So as a take-home message, I just want to remind that soil is foundation for nature-based solution effectiveness. We have to remind that soil and the nature-based solution relationship is bidirectional. And we have seen a rapid convergence in policy framework with the Green Deal, Nature Restoration Law, and Soil Monitoring Law. But at this moment, we have now a soil health definition. We have a first step for soil monitoring, but we have a critical gap is still existing, because indicators has to be harmonized, function-based, and inclusive of biodiversity. And we have to remember that advancing nature-based solution requiring the advancing of soil science and vice versa. Thank you for the attention.
Thank you, Eleonora, and thank you for the presentation that really helps us to understand why of this webinar, trying to connect the dots between different legislation that to become real, implemented, and have an effect on the ground, need to connect different science and different stakeholders. There is already a question of Christine, and also others are invited to ask questions that we'll try to address. But I think especially on ecosystem, about the definition on ecosystem of need of restoration and how this is assessed will be partially covered by the next presentation, because it's a member state level. The European Commission gives some guidelines, but then there is a problem or a challenge opportunity for member state to actually make plan that will be submitted in September this year on how to define, how to imagine a restoration plan, based also on the assessment of the degradation. So I think he's the best person also to take this question into consideration is Vito. That is the next speaker. Vito Emanuele Cambria is from La Sapienza University and Biodiverse Knowledge Hub, and is a plant ecologist and a co-founder of Rete Italiana for Ecological restoration. I don't know how to translate exactly the name of the network, but I think you are the best place to do so. So the floor is yours, Vito.
Thanks, Joanna. So let's share the presentation. Right. Here we go. All right, do you see it?
Yes.
Okay, sounds good. Okay, so good morning, everyone, and thank you very much to the ISINNOVA team for the invitation, for such a brilliant organization. Today I'm going to present two network of experts. One is a pan-European, it's the Biodiversa Plus Biodiverse Store Knowledge Hub, and the other is at a national basis, and it's called the Italian Network of Ecological Restoration, also RIRE. They are contributing to the implementation of the European Nature Restoration Regulation, especially this very important phase in which member states are preparing their national restoration plans. So let's start from the Knowledge Hub. It was launched in March 2024. It will run until September 2026. Its aim is to support member states with the implementation on the regulation, and at the same time to feed to the research and innovation agenda on restoration. It brings together 52 experts on both research and field products restoration. It is intentionally interdisciplinary. There are experts in the field of biodiversity, ecology, but also social policy and law science. This is because the regulation itself is not exclusive to the ecological matter. It is also about governance, planning, monitoring, and many other challenges. Of course, the timing we are coping with is very tight. The regulation entered in force in August 2024. The hub was already there, so the challenge started much earlier than indeed the entering force of the regulation. But at this stage, member states are working on drafting, as I said, their national restoration plans, and are expected to be submitted to the Commission in September of this year. The Commission will then assess these plans and asking member states to finalize, submit them after receiving some observations. After that, reporting will take place every 3 years. So we are in a critical phase. Decisions that are taken now will shape restoration policies across many decades. So this is why the connection between science, monitoring, governance, implementation is very important at this stage. So let's have a look on the work plan. It's pretty intense because the timeline is indeed very tight. So the Biodiverse Store Knowledge Hub is organized around three main principles. It should be evidence-based, oriented to the implementation, and rooted in stakeholder engagement. We don't have to provide only abstract knowledge. We have also to translate this into the decisions, procedures, criteria, monitoring framework, and support practical restoration measures. The hub therefore combines meetings, policy brief, webinars, scientific reports, And we also contribute to the official consultation of the European Commission, such, for example, on the template for the national restoration plans. Of course, we also promote dialogue events. So we are not aiming only to produce outputs, we also want to create spaces where research, policy, and practice can meet fruitfully. A good example is indeed this dialogue event that was organized in Paris in last year in May. The event brought together representatives from 20 member states, which are responsible for drafting the national restoration plans in their countries, and we worked together in 3 very intense days. It was a very useful opportunity to listen from them what they are facing in terms of practical difficulties and transforming such a legal obligation into a national planning document. We try to summarize all the challenges that have been raised those days and in a report which is available in the Biodiversity portal. I can summarize here very briefly. There are some challenges in terms of data baselines. As you probably know, many member states report inadequate or fragmented data, even inside the Natura 2000 networks, especially in marine and freshwater ecosystems. But this is even more evident outside the Natura 2000 network. This is a very crucial point because, as we know, the Natura 2000 network provided over the last decades the strongest platform for biodiversity conservation in Europe. It has generated experience, expertise, mapping efforts, and institutional knowledge. But the regulation requires us to go behind the protected area logic alone. It asks member states to restore degraded ecosystems across a wider landscape. This is super challenge, but from one side, we can use Natura 2000 as a strong foundation, but it cannot be a boundary. Outside Natura 2000 data, on the other hand, data is very much less harmonized. For example, habitat mapping is very often incomplete across many member states, so we have uncertain baselines. But however, we need identification of key parameters for restoration plannings. For example, the favorable reference area that might respond to Christine's questions in terms of how we define and assess those habitats would need more attention. But this is both technically and politically complex, identifying such a baseline. But at the same time, we have opportunity. We can improve our knowledge in biodiversity on soil data, but also we can have more citizen science, better modeling, centralized database that all together can support much better planning, prioritization, and reporting. We also have, as you probably have been aware of, many concerns about capacity governance. Many administrations have limited human and technical resources, and many responsibilities are often fragmented across many sectors. The regulations touches interdisciplinary. It touches environment, agriculture, forest, water, climate, and many others in sectors. But all of them works with different procedures. They have different data sets and very different objectives. So this can create the operational incoherence. For example, some cases even when a restoration is legally required and ecologically justified, implementation might be delayed by fragmented, very long authorization pathways, unclear responsibilities, sometimes even contradictory incentives. The opportunity is there is to strengthen interministerial and cross-border cooperation while investing in long-term expertise, training, and infrastructures. Last group of barriers and opportunities regard stakeholder involvement. Several countries, we know that there are sort of reluctance from primary production sectors, especially agriculture, forest, fisheries. But this is not to be retained as an opposition to nature. Very often it reflects concerns about the cost, administrative burdens, land use restrictions, but also lack of trust. A cause might be because the consultation process we put in place is often uneven. If stakeholders, for example, are involved too late, restoration might be perceived as a top-down obligation rather than a shared opportunity. That's why the communication is very important and above all must be credible. We need to communicate better the co-benefits of restoration for climate resilience, soil health, water regulation, biodiversity, and human well-being. But we also need to communicate the cost of inaction. We have to always to stress that not restoring ecosystems means more drought and flood vulnerability, soil degradation, and such things. So this is very important. That lend us to the today discussion. We have to combine different sectors to put in place such a piece of legislation. So very briefly, I want to show you some outputs of the Knowledge Hub. One is about this study we have been done in identify societal conflicts in nature restorations. And the study starts from the fact that not all the conflicts are the same. We started from identify 5 types of conflicts. I'm not going too much in details because of time constraints, but there are interest-based conflicts when the actors calculate cost and benefits differently. Rule-based conflicts when the policies of legal frameworks are inconsistent. Norm-based conflicts when the restoration affects local practices of social expectation. There are also ideological conflicts when there is a lack of knowledge beyond that, and as well as power-based conflict when the decision-making authorities feel excluded from the decisions. So, in many cases, these conflicts are mixed, but recognize them help us to better identify the process and be proactive. So at the moment, we are synthesizing across 14 case studies across Europe, and soon we'll publish these results. And adaptive management is also a critical process for streamlined restoration. Restoration is not a linear process because ecosystems respond in very uncertain ways. Climate condition change, social expectations evolve, some interventions will not work as expected. This is normal because the problem is not the failure itself. The problem is failing without learning. So the hub is working on adaptive management in a regulation context. This means that we have to provide practical recommendations for practitioners, policymakers, institutions to in that sense, in a way that the restoration can include clear objective, indicators, threshold, triggers, and mechanism to counter-react to changes in the restoration process. That's why we believe, and we are super convinced that the plans must be a living document rather than a fixed commitment. So also in this case, we are collecting case study from across the world, actually. So I can go a little bit further regarding this other issue that is about having attention to the production and movement of native plant materials. There can be an issue regarding the spread of pathogens inside the soils in all the plants that would be supposed to be planted down across the many member states is an issue. So we must be sure that the nursery have a very clear biosecurity plan. So this is another thing that we should pause attention to. I just want to go now to move towards the Italian network for ecological restoration. That somehow it's part of this broader strategy of Biodiversa in fostering the creation of national hubs. So this network was born again from the need to strengthen the policy, the research, the practices at the national level. We are bringing together experts from academia, public institutions, businesses, and we want to promote standards and good practices to develop a culture of ecological restoration. So we were pretty active. So from 2024 to nowadays, we had many meetings, conferences, meetings with authorities, audition at the Italian Senate, meetings with the European Commission, and we are now at the stage of supporting the the um, the the drafting of the Italian National Restoration Plan. So we are making our internal consultation, gathering all the feedback and comments on the draft that has been shared by the Italian Minister of Environment. So until June the 9th, this window for consultation is open. We are collecting everything. We will draft a synthesis and submit this in a positive way, how this can be improved. We will be joining the next Society for Ecological Restoration conference in Brest. We will have a special session on national networks like this and how they're supporting the process. Also, Biodiversity Plus is pretty active. We will be in Paris organizing a business and biodiversity workshop. We will be also in Davos at the World Biodiversity Forum, and of course, again at CR Chapter Europe conferences. We will have a final conference in September online, and this is a way to conclude the process, also to plan the forthcoming initiatives. The timing is pretty similar. September, the member states will submit the plans. September, we conclude the first stage of the hub. We'll see what next. So, to leave you, I just sum up some messages. The both hubs are working to improve the implementation of the National Restoration Regulation, but we want to keep a positive and constructive environment around that. The restoration should not be seen as only an administrative burden. It can become an opportunity, as I say, to strengthen the technical capacity, improve governance, support new professional skills, and create a stronger restoration culture across Europe. For this, we need standardized and operational guidelines. We need to harmonize the cross-sector framework in terms of governance, foster professionals with two interdisciplinary skills. This is because the restoration is not a one-size-fits solution. It must be tailored, adapted, and local managed. And we should provide that this exercise of drafting the plan is not become a cherry-picking exercise. Not easy win, please. And finally, and allow me a recommendation, we should not be shy about failures. We should not acknowledge the barriers, burdens, implementation difficulties is not a weakness, it's a condition for real progress. So my last slide is about try to combine, the point of contact between the Natural Restoration Regulation, the soil monitoring law. Of course, soil health is not an indicator of restoration. Success is a precondition for restoration to work. Without healthy soil, we cannot never reach our restoration targets. We can say that soil monitoring improves the diagnosis, restoration planning drives the actions. Together, we have to support credible, targeted, and adaptive national restoration plans. But we are part of the same cycle. We have to contribute to the creation of a restoration culture in our continent for a better ecosystems and why not more ethical societies. Thank you very much.
Thank you, Vito, for the great presentation. I think it gives really also data is a precondition, and then there is all this human policy stakeholder component that have to be engaged and to make really the action on the ground. And I found very interesting also the different kind of conflicts that can happen and how we have to tailor not just data, but also approach and communication depending on the community we want to work with. I think there are two questions, but if participants want to raise their hand we have few minutes because I think we are a bit delayed with time for a question for the two speakers. Is now a good moment, I think, to do so. I think they were very rich and diverse, representing, I think, the policy and governance and the need for us all to work on the coherence between how to ensure that we understand each other and proceed on using the indicator in the best way. I do see here a question for Vito. Written. I don't know if the person wants to speak up, and maybe there were before some questions for Eleonora that were more from a science point of view. I think partially you speak about this interactive process, because here the question is the restoration as prospective interactive process or dynamic interactive process. It's quite from a social science point of view. I think, I don't know if Vito, you have a view on this.
Ecosystems are not static processes. Indeed, they are very dynamic. So it should be dynamic, but then how to turn this from a piece of paper to something that follows the dynamism is a super big challenge. There are different kind of methodologies that the member states are putting this down. The Commission doesn't necessarily ask a single methodology to member states. You know, each states have different conditions, different way of thinking, different source of data. The important is that this should be, as I said, a living document, able to get the changes in terms of ecology and social aspects. So it's a challenge we'll see in the future. Yes, thanks for the question.
Thank you. And I see a question also for Eleonora. Which standards of soil biodiversity do exist, if any? Especially, is there a standard to DNA meta-barcoding of bacteria and fungi? So it's quite specific. I think you are muted.
It works?
Yes.
Okay. The problem, biodiversity means life, so it's difficult to monitor life. This is the way, the reason, because this indicator were the main problem about soil monitoring, because there is no standard, there is a lot of discussion in scientific literature about this part. We have this possibility to monitor, and these indicators has to be considered together in an interactive way with all other indicators, because unless they cannot work, because we need to know for soil health if the soil is, how the functional of soil is going on, not only which microorganism or fungi are present. The functionality of soil is the main pillars about soil health. And also the fact that these part are considered on voluntary indicators to be provided, and there is also the problem that not all these methods are harmonized at the EU level. This is the main problem about this monitoring law. There is a lot of discussion during the legislative ether of this. From this point of view, by scientific world, there was a lot of white papers about the soil scientists to the Commission to make them understand that biodiversity is the main point. But for the moment, there is a compromise. There has to be monitoring on a voluntary basis. And let's see, from in these years of we have starting from this that law has been entered in force, and at the first round about the evaluation, we see that these indicators became mandatory and which methods will be allowed to be used.
Thank you, Eleonora. And I think I do see a tension between, evidence from science and policy that try to how to go forward. I think soil monitoring law is not perfect. It will be revised in 6 years, and I think there will be a push to be more exact also and more comprehensive, and is far to be perfect, but it's a first step. So it's a compromise between what is possible, and I think it's a sign on the need of soil health data also for nature restoration. And I think there will be more time for question at the end, but as we have some time issue, I'm happy to give the word to the next speakers, also because she can give really a view on really soil assessment, and it's Christine Allewell, Professor of University of Basel of Environmental Geoscience and lead developer of Sherpa. So, Christine, thank you, and the floor is yours.
Yes, thank you very much for the invitation. Can you all hear me well?
Yes.
Yeah. Okay. Yeah, I'm happy to talk here about Sherpa. It's a very new soil health assessment tool. It's very new because it's one of the first tools being really quantitative. And I called this talk Sherpa in Action, Quantitative Soil Health Assessment Across European Soils, a possible contribution to SML and NRR. We will see at the end of this talk. We are a group of European scientists contributing to this. This is very complex, and not one person can know all. My main co-worker is, it's Surya Gupta, who is doing all the data acquisition, all the calculations, the programming, and the presentations of figures and tables. So we developed a soil health assessment key across different land uses. And while several approaches have already tried to quantify or at least qualitatively approach the soil degradation processes, be from soil erosion, landslide, contamination, nutrient surplus, pesticides, salinization, compaction, and carbon assessment. I think the new about Sherpa is that we really consider intrinsic soil health. So what is intrinsic soil health? Intrinsic soil health is basically if I go out with my students into a forest, into a cropland, into a grassland, and try to tell them whether this soil is actually as it is supposed to be or whether it is degraded. And what do I look at? In a forest, I would first ask myself, which climate am I in, geology, altitude, and then I look at the humus layer, and I probably, with 95% certainty, I can say this is a healthy soil. In the grassland, if I have excluded all the degradation processes, basically it's vegetation cover. If we have a full vegetation cover and we assess all these degradation processes separately, we can pretty be sure the soil under this grassland is healthy. Under cropland, we assess the fractional vegetation cover throughout the year, which means do we have any intermittent cropping, any mulching, is how long actually is the soil bare or not. We assess the soil structure and the percent of organic fertilizer via total fertilizer. So in addition to this intrinsic soil health, and I talk about wetlands at the end if I have still time, this is first for forest, grassland, and cropland. In addition to this, we look at the degradation processes as it has already been with the EUSO dashboard from the Joint Research Center. But we do it a bit more refined, a bit more, and a lot more quantitative, actually. All in all, a healthy soil with no soil degradation would have a +10. The lowest intrinsic soil health here in part 1 is from 1 to 10. The most negative scores degradation in part 2 is a -9, and then we subtract that, so the most negative score possible is a -8. Just that you are where we are at with numbers, but I will repeat that. Okay, so what can we do with this tool? I can't tell you all the details, it's too complex, but I just want to show you now a few examples what we did with this Sherpa assessment tool. We applied it to the Lucas monitoring data of the croplands with 3,500 data points, having all data available we needed. And we divided Europe in 4 biogeographical regions from south to western, central, eastern, and northern. And in the upper right here, you see the frequency distribution of the scores. And remember, +10 is a healthy soil. And what we see, and what of course we all know already, that European croplands are not very healthy. 99% plot below 5 and 85% plot below 2.5. What else can we see from the Sherpa system? We actually have in the lower right here the cumulative plot, what we call the cumulative score, where we subtract all part 2, negative scores from the intrinsic soil health of part 1. And this now tells you which processes actually contribute to this low soil health. The major threats are soil erosion, nitrogen and phosphorus excess, carbon loss, and pesticides. Of course, we know all that, but now we can quantify it. What we totally underestimate actually is compaction, because there is no data. So it doesn't really show up, and we all know croplands are highly compacted. So we need better data for that, but I think it's not a fault of the Sherpa system, it's more that we need better data. We also see a gradient from northern to central and western to southern soils, with the southern soils being the most negative, the most degraded. If we look at the grasslands, the Lucas monitoring data had only above 600 points where we had enough data to assess the Sherpa score. But the results are very similar, actually, not very healthy grasslands. If you look at the cumulative plot, the major threats are nitrogen and phosphorus excess. And actually, if you go out for a walk now in spring, you see exactly that. We have grasslands basically homogeneous with a few species. There's no herbs and flowers, but mainly dandelion and whatever. Yeah. So the Sherpa evaluations are pretty consistent with what we find in literature. Again, we miss compaction here. We applied the Sherpa to the ICP forest data with 4,000 level 1 plots having the data needed. 4,000 locations of level 1, but only 2,500 having the data we needed. Again, with the 4 geographical regions. And if you look here at the right side, we see, of course, that forest soils are quite a bit healthier than grassland and croplands, but around 50% have a soil health less than 5, 20% less than 1, and 15% even less than 0. And if we look what actually causes this soil degradation in forests, it's basically nitrogen and heavy metals, and this is also consistent with literature. However, of course, we do not consider climate, and we all know that forests at the moment heavily suffer under climate change. So prolonged droughts, late frosts, new pests coming in. So currently we try to evaluate the role of soils to the forest decline. So this is from the ICP forest data, the forest decline in Europe from 1990 to 2025. And very interesting, nobody really is talking a lot about forest decline. When I grew up, when I did my first steps in science, I actually did my research on acidification and forest decline. Everybody talked about forest decline. But then people decided this was all nonsense and nobody's talking about. But look at this. I mean, look, this is the mean defoliation from 1990, where forests were already degraded, to 25, I think it's the newest data, across the different species, and what an increase in defoliation. So our question now was, how much of this is low soil health and how much is actually climate change? We tried to untangle the role of the Sherpa scores in the forest health using GAM, generalized additive models. Not me, student. I'm not doing this. This is Surya Gupta doing. So these are the preliminary results. They're very preliminary, but they seem to make sense. So all these variables are statistically significant. What you see here in the upper left is that defoliation increases with increasing temperature up to around 15 degrees. Defoliation decreases with increasing rainfall to 1,700 millimeters. Then here you have the intrinsic soil health part. There is no clear relation to defoliation, which also makes sense. But we have a very clear relation to part 2, the degradation processes. So a clear increase in defoliation with increase in soil degradation. So certainly soil health and low soil health is contributing to this forest decline. But of course, this doesn't mean that climate is not playing a big role. Of course it is. We did another application within an EU project, Soil All Life, to olive orchards across the Mediterranean. Here you see the Sherpa application, the Sherpa score to these olive orchards across Greece, Italy, Portugal, and Spain. We also have orchards in Morocco, but since Sherpa is developed for European soils, we were not comfortable to apply it to Moroccan soils. What we see here is that the cumulative plot shows the highest degradation in Italy and Spain, followed by Greece, and then to Portugal. This is a comparison to the European croplands I just showed you a few minutes before. So you see that olive orchards are actually a lot more degraded than the average of the European croplands. And the major threats are again soil erosion, nitrogen, phosphorus excess, carbon loss, and partly pesticides. If we look at the regional distribution, though this is now the Sherpa scores across the investigated olive orchards. Blue and purple is the most degraded with -3 to 0. Green would be the least degraded, which doesn't mean it's healthy. It's still only a 5 of 10, right? So that was where most of the European croplands actually plot. But what we actually see is that it's very consistent from our observations. The most severe degradation is Andalusia and southern Portugal, followed by Sicily, then Crete and Lesbos and Greece, and the southern Peloponnese are kind of the best, but still highly degraded. And how does these orchards actually look like? They look like this. If you fly into Malaga, you see 10 million of hectare olive farming, even in organic orchards. It looks like this. This is not soil. This is weathered bedrock with trees on it. And it's just that the olives are so endurable that they cope with that. That we can, and actually the plan is to, I think, to increase these 10 million to 20 million hectare for sustainable food production. So I think we have to question that. These are pictures from Kefalonia, actually, the Ionian Islands in Greece. And these look very different. Of course, I picked nice pictures, but I mean, nature-based solutions might be simple and effective, and it's more a question of tradition and misbelief, I think, that farmers think that soil vegetation is harming the trees, is taking away water and nutrients from the trees, which is actually not the case. It's actually protecting the soil water, it's protecting the nutrients. So I think there is a lot in communication to be done to protect these systems. So if I have time, a few minutes maybe on the wetlands. I see there is a talk after me on wetlands, so I will speed up a little bit. We have not developed the key for wetlands yet, but we're thinking along the lines that we say the intrinsic soil health in wetlands is basically about whether or not the wetland is drained. And then the part 2 scores, of course, is nutrient input and so on and so on. So the question was, how can we map natural and drain? Because the databases existing are not very good. So we tried actually to map between drained and natural wetlands from remote with the NDVI and the greenness index. And we find very consistent differences, statistically significant differences between drained and natural peatlands. For both NDVI and GI, for open and sparsely treated site. Of course, we can't map forested wetlands. That's from the remote is not possible. We find the same for albedo and EVI, even though it flips between open and sparsely treated site. But yes, we can. And the good news is we started with PlanetScope data, which we had available in the AI for Soil Health project, but now we do it with Sentinel and it also works, which is free and available. So I think we are getting there to map Europe. So my conclusions are remote sensing and biogeochemical indicators build a robust framework to distinguish natural versus drained peatlands. Now we have to develop the Sherpa Part 1 scores for wetlands. Sherpa is good in finding consistent results for cropland, grassland, and forest soil health and the major threats. Each of the parameters now has to be tested, validated, improved by experts, and we are continuously updating Sherpa. So we published the first version of Sherpa in January this year, and we already revised it twice, and I think it's a very complex system. It's not a difficult system, but it's complex, so obviously. And so we need now people to apply it. We need experts to join us to improve each of the tables and to critically test it. I think we don't really have a problem with Sherpa, but with data availability. At the moment, we only do point evaluations. We don't map. Because we need better data on soil structure. We need site-specific pesticide input, which is not available. We are just taking rough estimates. We need site-specific fertilizer input, which is not available. We need compaction data, which is difficult. And we need humus layer information in forests better, and also disturbance of humus layer. But generally, Sherpa seems to be suitable to assess soil health. And after careful assessment, it might be suitable as an assessment tool for the SML, I think. And as soils are the basis of all ecosystems, as we have already seen this morning, a quantitative monitoring of soil health with Sherpa might contribute to the NRR. Okay, the Nature Restoration Regulation. Okay, so many thanks for listening. And I'm happy to take questions. Actually, I already see the question on soil biology. I always get the question on soil biology, and the answer we already heard this morning. I'm not saying soil biology is not important, but we don't understand it. So we can't include it in these systems because we can assess now, we are good enough from a scientific point to assess microbial communities, DNA barcoding, but we don't know what it means. So we can't really relate it to soil health yet. But Sherpa is an open system. It's programmed in R, and it's meant to be continuously improved and revised. And as soon as we are there, we will, of course, include biology. But I have to say that as a soil scientist, I use soil structure a lot to assess soil biology. If I have an adequate soil structure, for instance, a granular structure or even subangular, I know the soil is healthy and the soil biology is working well. And if I have the correct humus layer I expect in a forest, I know soil biology is working and everything is in order. So this we have, but that doesn't mean that soil biology should not be considered better in future. Okay, thanks a lot.
Thank you. Thank you very much. I think it was great to see how to read that, how to, progress on science can in medium long term become also policy support tool. I think we are going this direction, and also I think it will be great, the collaboration of different science to use, understand, get to know how to communicate data. And thank you for this very, very comprehensive overview of, but we all need to study more, understand better, to communicate in the right way. But I think it really offers a tool that can support. We move to the next presentation. There are a few questions. Also, we hope to have some time after the next presentation to go back to a question that is from Vince Chu Wu from University of Aberdeen School of Biological Science, and he will presenting a modeling impact of management practice in soil carbon in peatland forest system. So thank you, and Vince, the floor is yours.
Yeah, thanks, Giovanna. Don't know if you can hear me loud and clear. Yeah.
Yes, and
Okay.
we can see the presentation.
Oh, perfect. Yeah, thanks once again, and also to your team for the invitation to partake in this important discussion. And also a big thank you to all the speakers that have taken time to present lovely and interesting talks as well. And it's good to see what's happening around the world and across Europe, how much effort being put in science for aim at restoring our nature, and both the peatlands, the soil head, and different part of the ecosystem. So yeah, Christine, this similar talk to what I'm going to say now, but though in a different perspective. She already did a brief introduction of my talk on peatlands. So basically what I'm going to do now is very brief, because the time is quite small to give a detailed talk on what we've done. And peatland forestry is quite an elaborate one, comprehensive thing, and a lot of time needed to give more detailed discussion. But I will just present more like a snapshot of the output from the previous project that we did in the Holy Soil and project, which is another Horizon project as well, where we applied the ECOS model developed by Pete and Joe in Aberdeen to simulate different management impact of a peatland forest in northern Europe. So as we all know, for those that have interest in peatland, how much they contribute with respect to emissions of greenhouse gases into the atmosphere, and different methods have been adopted by different stakeholders, how they can stop, mitigate these emissions, both from peatland soils and also from forestry as well. And we, at our own level of science, the ECOS model have been applied by different researchers in our modeling group to simulate the different impact of a European peatland soil with respect to CO2 emissions and also soil organic carbon stock. And in forestry management practices, there are different methods being adopted by forestry owners, and in order to manage their forestry for different purposes. It could be for increased timber production, it could be for to increase biomass, and it could be also for to reduce emissions of CO2 from their forestry. But for this field experiment that was established in Letuso and the Rascalopi, so they adopted two main harvesting methods: the clear cut and the selection harvesting, that involve the clear cut involves removing the entire forestry, while the clear cut involves selection harvesting of different trees, leaving the particular biomass, and most times residue is being left in the field. So in the figure here is just trying to show us the mature forestry, where we have both the emissions to the atmosphere and also carbon sink as well. But however, when we made decisions to adapt these two main harvesting methods, the clear cut, which involve removing all the trees, that's usually high CO2 and methane and NO2 emission to the atmosphere compared to the selection harvesting. But some years after, when the trees began to grow back, then there's obviously some level of activities going on who could either affect to reduce or increase the CO2 and the methane and the NO2 emissions, which further highlights the importance of these different management practices with respect to reducing greenhouse gas emissions and also sequestering soil carbon in the forestry. So the center here shows the mature forestry, while the down one here shows when the forestry have been done through selection harvesting, and then we have the clear cuts, and they all have varying impact with respect to how much carbon is emitted to the atmosphere and how much carbon is being taken down into the forestry through these management practices. And they varied over the years until when we have a mature forestry again, probably after 20 years onward. But for the purpose of this field experiment, so a field site was established in Finland and in two sites, and in this site, they selected two main harvesting methods, but different sites. We had the first site is the control, where the forestry is being left without harvest. We have the second site where we have the forestry is being harvested completely, almost removing the biomass nearly 100%. And we have the third site where we have the selection harvesting, where the forestry is being harvested up to about 75% of the biomass is being removed, leaving the residues on the site. And then within these 2 years, this period of harvesting method, the gas flushes from this site, we are all measured using the manual chambers. And so what we did was to use the data from this field experiment to run our model, do the basic model simulations. And based on the output, we went further to do the model validation. And based on the success or the degree of confidence that we have from this validation, we now went further to apply this model to predict the impact of these two management practices with respect to CO2 emission and also the soil carbon sequestration in a future climatic condition. The result is what I'm going to present in, but just a brief description of where the data we use in the modeling exercise was obtained from. And now ECOS model, I know some of us have heard about the ECOS model. ECOS stands for estimating carbon in organic soils, sequestration and emissions. It's quite different from other soil-based process model because it's able to predict both soil carbon and the CO2 and the methane emissions in highly organic soil using just very simple input to the model, and basically the weather data, which is rainfall and also which is rainfall and temperature. Unlike most complex models that require more data input, but using this commonly available data, this model is able to make prediction that can be used both at the regional and also at the global scale to make predictions that give us an understanding of impact of different land management, land use types across arable land, across grassland, across forestry, and also and the peat vegetation, how they impact the soil carbon sequestration and also greenhouse gas emissions, both at the interim and in a future climatic scenario. So the model has been validated across different sites. So we now take a step further to apply this model from this side and just to achieve two major aims to simulate the impact of the different harvesting methods across these different drain peatland sites. And then we now determine the long-term impact of this different harvesting method, how they impact soil carbon sequestration and the emissions of CO2 from this site using future weather data. And the first step here gives us an idea of the data that was used as input in this model. Of course, the soil carbon, the pH, and the bulk density across different depths from the different harvesting method and also the control both in the two sites So we use this data as input in the model to run the simulations and then compare the result of our model output to the measured data from this site and carry out simple statistical analysis to determine the result or the evaluation before applying this model in a future climatic scenario. And we also use the plant data carbon input as well from this site to run the model, where we have three years of data being measured from this site, from the control, the clear cut, and the shock harvesting as well. And as you can see, they at the beginning of the experiment, we had the control. So we had higher input from plant litter into the soil, but this increased immediately the harvesting method we are establishing the site. But after a year, they experienced some sudden increase as well, which gives us an understanding of the impact that harvesting could have with respect to litter being deposited into the soil. So now, based on result of our simulations, we carried out a simple model validation to understand how the measured data fit into the simulated output from our model. And the site, so we basically look at two things here: the trend both from the simulated output and the trend both from the measured output. And also we look at the peak across the two different scenarios. And as you can see here, the model successfully modeled these emissions of CO2 across the site, both from the control and across the two different harvesting method. But there are two major striking things here. One is that the model seems to be predicting accurately what is happening at this field during outside the peak time, because when it's peak time, the model seems to be giving higher evaluation, higher values compared to the measured value. But outside the peak, then the model seems to be spot on. And also, interestingly, the model was also able to predict the seasonal changes, just like it was measured in the field. For example, during the summer period between June to August, where we have higher emissions of CO2, the model was able to predict that as well. And during the colder period, like from the beginning of autumn to the summer, when there was a drop in weather, which also affects the drop in the CO2 emissions, the model was also able to predict those drop as well. So those three different points gives us a clear indication that the model is able to predict the behavior of the emissions across the two sites and also different harvesting method, both at the off-peak era, both the seasonal trend and also following the same patterns of emission across the years that the data was measured, collected from this site. So we also, this is the arrow. So at this point here is where we have the off-peak, when the model was giving more accurate prediction than at the peak time, when there was cases of the model giving higher values compared to the measured value. Then we did simple stat analysis, the Pearson test, to carry out the model evaluation for us to understand if the model is biased or not on this side, and also for us to understand if the degree of association between the model and the measured value is different or not. And based on that, when the value of the degree of error is less than the degree of confidence, that means that the model bias is not taken to be significant. And we also check a degree of closeness between the model and the measured value as well, to check if they are also significant. And that also gives us an idea that the t value across the site, exception of the clear cut and the control, but we are all less than the t value at p is 0.5. Do also tells us that there is a close relationship between the model and the measured value across this site and also across the management systems. And we also look at the air value, and the air value also at a critical at 5%. That also gives us an idea that the model output was spot on across different indices that we checked to be sure that the model could be said to be applicable in this site. Now, based on the result of our evaluation and also of the simulations, and we also check further to do a simple plotting where we look at the one-to-one line and between the model and the simulated value and the measured values to look at degree of correlation between them. And as you can see, across all the site, apart from the clear cutting and clear cutting side, the model seems to be also flowing the same trend with the measured value from the one-to-one line, which also give us a strong indication or confidence that the model could be applied in this site. Now, based on all this result of analysis, we now did a future prediction about 50 years to understand if we adapt this particular harvesting method across the two sites, what will be the impact with respect to CO2 emissions compared to the control when the peatland forestry is left without harvesting. And the key message here is that the behavior of the model and on this prediction over the 50 years period varied based on different sites. And based on from these two sites, they have different soil carbon content. They also have different dominant species of tree, and all those factors influence the emissions of the CO2 from this site. For example, the first site, we can say that immediately after the 5 years of harvest, there was a little emissions of CO2, rise in CO2 emissions. But after these 5 years, we experienced a drop, and they continued to drop until after 20 years when one of the management practices, which is CCF, led to a sudden rise and the highest rise in CO2 emissions after 20 years. But the good thing is that the rotational harvesting remained lower consistently across the 50 years period. But after the 20 years, the CCF that led to highest rise in emissions now decline, and they continue to decline almost to the same level, to the same trend with rotational harvesting. However, the control continue to increase and decrease consistently, but it remain higher than the two different harvesting methods. But on the contrast, we have the same behavior was experienced on the reverse at the Tuso site when the control remained lower consistently all to the years of simulation for the 50 years. But the two harvesting methods led to a sudden spike in CO2 emissions and continued to decline consistently almost up to the levels of the control over the 50 years period. So that means that the two harvesting methods, although they led to decline in CO2 emission, but however, either the increase or decrease in CO2 emission is dependent on the site. And because the site have different ecological characteristics, have different soil data, and so on. So all those factors are driving forces that determines what happens at the site with respect to CO2 emission. Now, we also try to understand what is also happening with this soil organic carbon sequestration after 50 years according to site with respect to the different management practices. In the first site, so we experienced that the continuous cover forestry led to a more increase in organic carbon compared to the clear cutting. But conversely, in the Lotu site, now the clear cutting led to a higher increase in organic carbon compared to the continuous cover forestry, which also tells us that the site also determines the behavior of the different harvesting method to decide if they will lead to an increase or decrease in soil organic carbon sequestration. And therefore, based on all these simulations and the behavior of the model, the key message here is that we are confident to apply this model across the site and management to simulate soil carbon sequestration and also emissions of CO2 based on the good correlation between the measured and the modeled value across different sites and also management. But however, the rotational forestry seems to offer more longer term potential to reduce CO2 emissions and also increase organic carbon sequestration as one of the sites. But however, the clear cutting led to greater soil carbon sequestrations than the rotational forestry in the two sites. Therefore, the choice to decide if we adapting clear cutting or if you're adapting the rotational forestry with respect to either to increase soil organic carbon or reduce CO2 emissions is dependent on the site features and characteristics, which could be maybe based on the dominant tree species in those sites. A recent work by one of our colleagues also confirmed the same thing based on the field data about 8 years from these two sites. And it was observed that the sites that have dominant tree-rich species like Norway spruce seems to be more prone to having lower emissions compared to the site with more poor species that are poor in nutrients, like the spine trees. But that is subject to scientific discussion. But that is just the key take-home stage that we have from the exercise. Yeah, thank you.
Thank you very much. Very interesting and complex. I'm afraid we are running out of time, but I didn't want to interrupt your presentation. I thank you also, Christine, that answered to some question, and we were saving time because we also don't want to go too much longer, also because it's lunchtime in many countries. But just in case there are some quick question for Vince, if you have question, you can raise your hand or quickly. I just think to what extent you have already try to use it at local or government level, this kind of projection to give recommendation for also for management practice, or is still too early, is something that you plan to do?
So is that for me, Giovanna?
Yes, yes.
Okay, yeah. So yeah, we're always making recommendations based on the findings from our modeling, both at the local and also at the regional scale. But then, as a scientist, the best we can do is make recommendations. It's not left for the policymakers to adopt such recommendation that we have made based on the findings from our scientific research. So I believe most of the key stakeholders that are quite, because I believe the Holy Site project was quite a massive one because there was so much interest from forestry owners, from landowners, from policymakers to understand how much impact that managing forestry could contribute, reducing emissions, while at the same time retaining the output from this forestry management. It maybe because as a forestry owners, my aim is to have higher yield from my higher tree biomass from my forestry. But from the government perspective and my own area of research, I want to see this forestry being able to reduce emissions to the atmosphere. So it's always like a win-win, like a trade-off thing between the two scenarios, where we are being careful not to adopt a system or a practice that would, although reduce the emissions, but lead to decrease in the yield of the forestry, both in the tree biomass. So at the end of the day, there always a trademark, and the best decision has to be made based on the country, based on the region, based on the interest of the owners, whether it's a private forestry, whether it's a government established forestry, and what to do so that we're able to have the best decision that can favor everyone.
Thank you. Yes, we go back to the interest that there is on the function of the ecosystem. I just have a few slides to closing this webinar, and thank you all that stay with us. I just want to highlight that this is a part of a series of webinar, and there will be 4. And the next one that is particularly hot and difficult is on soil health and agricultural policy. Then there will be soil health and climate and carbon policy, and the final one on soil health and water nexus. The next one will be chair and let's say organized also by Joe Valtila from UK, and there will be the participation of Manuel Petel from the European Commission and Simon Kramer from EARA. We're still waiting for confirmation for the final speaker, but will be next Friday, not in 2 Friday, always at the same time. So for those of you that are interested to see soil health in the different policy, we imagine that we invite for a block also 1 hour and a half into Friday from now. Final things, we have created a form to get feedback, suggestion, ideas from the participant, and we'll be happy to get your suggestion and feedback also for the next 3 events. So if you have a topic or practice that you think we should explore, suggest. I'm happy to know more also about the participant. Thank you all for the great speaker. I think they made a really interesting ensemble of different perspectives on soil health and also on the challenge that science, policy, activists face on trying to put something on the ground. I really think the dialogue between different stakeholders, different science, different setting is the only way forward. So really thank you for the speakers for this effort and their time and all the participants. And I hope that is the beginning of a collaboration, is not the end, as the end of Casablanca movie said. So have a nice weekend to all. Thank you.
Thank you. Bye, everyone.
Bye.
Bye.